Well, I'd like to begin now by telling you more about what EEMDL is. Welcome to the annual event. Professor Ravikumar and I are going to describe for you in initially broad terms and then a bit more specifically about what we're trying to do with EEMDL. And so let's go ahead and begin. We're all here because of methane, and all of you are familiar with the challenges associated with methane releases to the atmosphere. Methane's responsible for about 25% of the total warming due to changes in the composition of the atmosphere since the start of the Industrial Revolution. We're all familiar with that. And as Roger mentioned, if we look at the total global methane budget, the methane releases from the energy sector are about 100 teragrams a year, 100 million tons a year. That's about a third of the man-made emissions, which in turn are about 60% of the total methane emissions to the atmosphere. So we're all familiar with this, and I'm not going to belabor this point. This is driven, though, global, national, and other goal-setting activities. And so at the global level, we have the Global Methane Pledge that emerged out of a recent COP, a conference of parties. So countries representing about 45% of global methane emissions have pledged to reduce total methane, not just methane emissions from the energy sector, but total methane emissions by 30% by 2030. And a disproportionate portion of that is going to come from the energy sector. So there are global goals. There are also state goals. Colorado, California, New Mexico are undertaking state initiatives, different scale, but driving methane reductions even lower than the global pledges, even lower than national pledges. There are sector goals. So the Oil and Gas Climate Initiative has announced multiple goals. There are multiple other organizations that have set goals for reducing methane. Again, somewhat different scale now, but looking at the sector as a whole, and what you're seeing here is elements of the pledge from OGCI and reducing methane to near zero by roughly 2030. Companies have also made commitments as part of this pledge. So sector-specific goals. And then there are supply chain goals. So organizations like One Future, very early in the process of looking at methane, made commitments to reduce methane emissions along entire supply chains to 1% or less, and in fact have overachieved and are now getting to roughly 0.5% along entire supply chains. All these are at different scales, so we have complex goals at very different types of scales. We all know that if you have goals, you'd better measure. And what we're going to be talking a lot about over the next 2 days is how are we going to measure progress towards these goals? And we're going to need to do that at global scales, at state scales, at the company, along supply chains, multiple different scales along which we need to make measurements. So what measurements do we have? Well, if you look back 10 years to when some of us in the room were first making these measurements, we didn't have many, and they were really expensive, and they were hard to do. Often we were making measurements for the first time. Here are a couple of pictures from a decade ago. Some of you in the audience will recognize the people in these pictures that we made measurements in the field with. And so we used to have to go directly onto the sources and make measurements. That was a decade ago. Now, in 2023, we have a whole portfolio of different measurement types. We have, and continue to have, the on-source measurements, but we also have on-site fixed monitors. We have cameras. We have aircraft flying various types of technologies. We have vehicles that are equipped with measurement technologies. We have satellites and more satellites coming. So we now have a powerful portfolio of measurements at multiple scales. And so Let's think briefly now, if we have all these measurements, what are we trying to measure? And so I'm going to think about this at different scales as well and present this to you at different scales. So think of this 2x2 matrix. And along the vertical axis, we have large numbers of sources of emissions that release at a relatively small rate. We have a small number of emission sources that emit at a relatively large rate. We have, looking at the columns, both routine emissions that we keep track of, inventory, report, but we also have unintended emissions, which we may or may not be able to effectively capture with our emission inventories. And then all of these four categories might be either continuous emissions or intermittent. Short duration, longer duration, a very complex picture. And so let's look at some pictures of that. And again, going at different scales. So I'm going to look first at a little animation here. Since we're in Texas, let's go to the Midland region and zero in on a subregion. And if we were to go to a site producing both hydrocarbon liquids and gas, what would we see? And so we're going to see a little cartoon, not an actual site. But what we would have is fluids, water, hydrocarbon liquids, gas coming out of the wellhead, going into a separator. And the flow from that separator would be controlled by pneumatic controllers that typically would intermittently vent as they opened and closed valves from the separator, creating an intermittent but small release rate emission. But there are 1 million of those nationally. Right? And that would control flow to the tank. Methane might flash as it goes to the tank and be released to the atmosphere, or as you see on the right, might be controlled and recovered. We might also have continuous emissions from things like pneumatic pumps that would be running to perhaps inject anti-corrosion fluids into the pipe. And so we have those emissions. All these are expected emissions. We could inventory them, keep track of them. And then we would also have, for example, leaks, fugitive emissions that would be unexpected, undesired, and we'd need to keep track of those as well. So if we were to look at the time signal from this entire site, we would have all these different sites with different temporal patterns. And if we were to look at the emissions from the site as a whole, we would see this very complex spatial temporal pattern. And if we tried to break that into individual sources, what we would actually see is that the sources would change from minute to minute. What's important in 1 minute, if we make a measurement over a 1 minute period, might be different a few minutes later, depending on what's being emitted at that time. Complex signal, even just from the single sites. Okay, and so you'll see here additional pie charts. Let's go on to the next. So what would this look like at a basin scale? Different basins are going to have different characteristics of those emissions that we saw in that 2x2 diagram. Large emissions, smaller emission rates, but large numbers of sources. In some basins, that will be a dominant part of the emission pictures. In others, it'll be a very small amount, even just in Texas. If you go to the Permian, the large emission events are a big part of the total emissions. Go to East Texas, and there are almost none. Go to the Barnett Shale in north central Texas, what would you see? You would see something that looked like this. So let's go to north central Texas, go to the Barnett Shale. What would a time series of emissions look like? And what you're seeing in the white lines there is county boundaries, looking down on little grid cells that are about a few kilometers by a few kilometers, so basically individual sites or small groups of sites. This is what the temporal signal is that we're trying to characterize at a basin level. Right? Complex to capture with snapshots. Right? We can zoom out to even larger levels and say, all right, well, this is what's happening at a basin level. Where does that methane go? Methane will persist in the atmosphere. It's a short-lived climate forcer, but in this case, short-lived means 10 years. So where does it go? Well, let's look. Dan Cusworth is here. Dan and his team from Carbon Mapper measured large numbers of emission events in the Permian. If we take those events and then say, how would those be transported at a continental scale? What you see here is wind vectors. This is what you would see. Right? Again, a really complicated signal. So at all scales, our measurements are going to give us really complicated signals that we're going to need to interpret. They're very powerful measurements, right? But complicated. And we're going to need all of those tools, that entire portfolio of tools, plus data from the operations of the site, knowing when we have tank flash, knowing when we have pneumatic controllers venting, and so on. We're going to need all of that activity data from the sites to help inform our estimates of what the emissions are and to interpret these very powerful data that are now emerging. So we're going to need to reconcile and integrate data from multiple measurement tools at multiple scales. And then we're going to need to match that to our goals. So no single solution is going to match up with all of the goals, or even any single combination of solutions is going to match up with all the goals. We'll have to match our measurements to the objective that we have. Our objectives are at multiple scales, our measurements are at multiple scales. We're going to have to combine those intelligently. So we're not the only people looking at this. Large numbers of you in the room are looking at this problem. And so what has developed over the last few years is this complex ecosystem of existing initiatives. The investigators affiliated with EEMDL are integrated into many of these, but not all. We've labeled in green those that we have some sort of affiliation with, but there are many, many of these. You can test your knowledge of the methane ecosystem by seeing if you can come up with what the acronyms mean for all of these. All right, but it's really complicated right now, and lots of people trying to understand what these ecosystems will tell us and trying to invent systems. All right, so as we've interacted with many of these efforts, the EEMDL investigators, we see common elements and common needs across many of these initiatives. And what we're going to need is a toolbox. All right? We need tools to interpret all these measurements and apply them to our diverse goals that we have. And I'm going to tell you a little bit of a story here that's an analogy. So I'm an avid cyclist, bicyclist, and I like to race my bicycle. And so when I first started racing my bicycle with my son, I insisted that he really understand the engineering of his machine and that I understand the engineering of my machine so that we could be as effective in the races as possible. So we went up to the Olympic Training Center at Colorado Springs and became certified bicycle mechanics. And so I used to keep my diploma as a certified bicycle mechanic in my office. And what I learned from becoming a certified bicycle mechanic is I walked away with a 1,000-page manual. Here's step A, step B, step C, step D of everything that you do to fix a particular problem. And we have the analogy here in the methane space. We have protocols. Do A, do B, do C, do D. All right? And you'll come up with an effective approach to addressing methane emissions. But what we're missing is the tools. And so if the bicycle repair manual says remove your chain, right? If you don't have a chain removal tool, you're out of luck. Right? If your wheel's a bit wobbly and the bicycle manual tells you fix that wobbly wheel by tightening the appropriate spokes using a spoke wrench. If you don't have a spoke wrench, you're out of luck. Right? What we need in the methane space is we need these tools. The tools need to have certain characteristics. Characteristics we're showing here on the left were developed by the US National Academy of Sciences as part of a study that they did on decision-making for greenhouse gases. These tools need to be usable. They need to be timely. They need to be transparent. They need to be scientifically credible and peer-reviewed. They need to be complete. We need a whole variety of these tools. And these tools then can be applied just as your chain removal tool can be, just as your spoke wrench can be. They need to be applied across many different applications. And you need to bring a toolbox to solving these problems. And so EEMDL's goal is to be that toolbox for the community. And so just to give you a very specific example of this, what we mean by this, I'll use this example. So we have a number of projects that EEMDL investigators are affiliated with that utilize continuous emission monitors. So I'm involved with something called Project Astra, which is working out in the Permian Basin, thinking about shared networks of continuous emission, continuous monitoring systems that are shared among multiple producers. And to interpret those fixed methane sensor data, we need dispersion models. We need to define how we're going to say an event has occurred. We need a whole series of tools. We're doing very similar projects in the Marcellus, but the same dispersion tools might not work there. And we're going to develop bespoke tools for the Permian. We're going to develop bespoke tools for the Marcellus. We're also doing projects with Cheniere for what is called the QMRV project to look at entire supply chains. And the tools that we'll need at specific points along the supply chains will be bespoke driven for those facilities. What we need EEMDL for is to take everything we've learned about those and consolidate them and generalize them, and then make them broadly available to the community. That's what we mean by a toolbox. Right? And there are many examples of this. Continuous monitoring systems is just one, many examples of this. And so specifically what we'll be doing at EEMDL is, I'll start with the models and tools, which is the second element here. We're creating these models and tools. You don't create models and tools in a vacuum, you apply them to data. And so we're generating data sets, aggregating, anonymizing, making public as appropriate from all the projects that we're working on, data sets that can be broadly available to the community. And then we're training and educating and creating user groups for these tools that we're creating. And then finally, and very importantly, we're doing organizing and convening. Right? And so tools, if nobody uses them, are not going to be effective. We need common tools. And so among things we'll be doing are organizing annual meetings, but other events as well to come to community consensus. And so we're going to be continually throughout this meeting asking for your input. So in front of you, you have a little index card. We're going to start this engagement by posing the following question to you. And what we want you to do is write down an answer to this question on your index card. All right? So I've described to you the current situation, the goals that we have, what the measurement signal is that we're trying to get, what some of our tools are. As all of us who are active in this space knows, in 2 years it'll be different. In 5 years it'll be different. In 2030, if we're successful, maybe there's no methane emissions from oil and gas supply chains. So in 2030, write down your thought about what should we be measuring? And I'm going to give you maybe 20 seconds to do that. What should we be measuring in 5 years? All right, let's do another element that hopefully will promote a bit more engagement, and then I'll describe the third element that we'll do. But why don't you share with the person seated next to you what you wrote down on your index card. So take a minute and talk about, with the person seated next to you, what you did on your index card. What do you think is important? Okay, so the final thing that we're going to do is collectively get all this information from you. So I've started something that I can't control here. And so if we could get your attention back, what we're going to follow up with on this is we want to get a sense of the room, not these pairwise interactions, but a sense of the room. So when you take a break, there will be flip charts. Get your coffee when we take our break, but migrate to one of the flip charts. We're going to have people who are going to be aggregating what your ideas are. We're going to do this throughout the meeting and other types of interactive activities to really get a sense of what you're thinking as well as us talking with you. But what we'll go to next is to talk a little bit about how did we get started. So we've been active for a year. How did we get started? What projects did we begin with as we take the first steps to getting to these 5-year goals? And so my EMDL co-director, Arvind Ravikumar, is going to walk you through what we've been doing in the first year. Highlights, you'll see a lot more about this as we go through the meeting.
All right, thank you, Dave. And thank you all for coming. It's a pleasure to host all of you here at UT Austin. You just heard about what EMDL's broad goals are, how we started, what are the key issues that we are trying to work together on, and how are we bringing the community together to think about solving some of the biggest challenges that's still outstanding in the methane emissions world. What I am going to do in the next 20 minutes is to give you a very quick glimpse of what we have been working on for the past 9 months or so. I'm not going to be comprehensive over the next 2 days. You're going to hear a lot more from our scientists, from our researchers, from our graduate students, and you can ask your questions to them. You can give your feedback. As Dave mentioned, this is going to be a very interactive conference. We're going to ask for your feedback and your thoughts throughout these 2 days. And what I'm going to show you here is a preview of some of the key ideas and the key project areas that we've been working on. I will show you animations. I will show you videos of some of the projects that we have done, and I will show you some actual data that we've been collecting. Again, these are umbrella of different projects, and you will see a lot more of them over the next 2 days. So what did we start working on when we first launched EMDL? And all of our projects can now be categorized under sort of 5 broad categories. You saw some earlier when Dave was presenting. We have a lot of work that's ongoing on using continuous monitoring emission systems. Like, how do we monitor and measure and quantify methane emissions from our oil and gas supply chain? We have projects that focus on emission event statistics. Many of you in the audience might be aware of new regulations from the EPA focused on methane emissions reductions, as well as updated reporting guidelines, all of which place an emphasis on understanding the temporal nature of methane emissions. How intermittent are they? How much emissions do we have? What are their duration? So we have a whole host of projects focused on emission event statistics. The next project, and it's something that almost every operator in the US and even around the world are thinking about currently, are operator and basin level emissions reconciliations. Okay, you go out and do all of these measurements. You might use satellites, you might use aerial systems, you might use drones, you might use other technologies. You have all of those measurements, and then you have what you report to regulatory agencies. In the US, it's the EPA, but almost every country has some kind of reporting system. And what we have found over the past few years of research is that the measurements do not match the reporting. And so why is there a gap? Can we reconcile what we are learning from all these new technologies with what we are actually reporting to regulatory agencies? So there's a whole host of projects that you will learn about over the next 2 days across the country, in the Permian Basin, in the Marcellus Basin, as well as in the Denver-Julesburg Basin in Colorado, on how we are tackling this problem in very different resource areas. The fourth group of projects focus on life cycle emissions models and methane census. This is the place that brings all of the measurements and all of the work that we've been doing in different basins, different operators and different parts of the country together. There's been a lot of work thinking about how can we standardize emissions reporting across the world, across different natural gas supply chains. And what you need to do there is to effectively put data that we collect disparately from the production side, from midstream, from liquefaction, from pipelines together to develop supply chain emissions estimates. How do we do that? How do we put all of this data collected using different technologies, collected at different points in time and different places together to develop the supply chain emissions. And the last thing is site monitoring and design tools. Right now, we are in a lucky place where there are tons of different technologies that an operator can choose from. Which one do you choose? And after you choose them, how do you design a monitoring program to get you the right information you need? So we are developing a suite of monitoring and design tools that help stakeholders think about what kind of monitoring do they need to put in place, what kind of technologies do they need to choose to achieve their goals, which can be very different. Some of them might want to reduce emissions as fast as possible. Some of them might want to get a more accurate inventory of emissions from their facilities. So depending on your goal, you want to match that with the performance of different technologies and select the right technology for that. So we have a whole host of projects focusing on design tools. What I'm going to do in the next 5 minutes or next 10 minutes or so is to give you examples of 3 different project areas. And these are all going to be in terms of animations. Some of them use real data, some of them are simulations, some of them are just illustrative purposes. But the idea is to show you what our students and researchers and staff have been working on for the past year or so. All right, so the first thing I'm going to show you is a video of how continuous monitoring systems at oil and gas facilities detect methane emissions. And this is a really complex problem because you have to think about atmospheric dynamics, you have to think about the site layout, you have to think about the emissions on the site, and you have to think about what do you make sense of the data that's going to come from these sensors. So what you're seeing on the video is a site, and this is now a model of that site. You're going to see different colors pop up, which refers to different sensors. Now, this is one of the sensors. If the wind is not blowing in the right direction, the sensor does not see anything. But when the wind goes towards the sensor, you can see the blue lights. And now there's a second sensor that came up on the bottom. And so the bottom colors is shown by orange. So only when the wind is blowing over the orange sensor, you're seeing the sensor detect something. And then you can have multiple sensors around a site. So if, for example, a third sensor has now come up, that's shown in yellow. That's on the right side of the site. And again, wind blows in all different directions. And so you're only getting data at that time when the wind blows over that sensor. And so you can see some of the complexity of methane emissions detection by continuous monitoring sensors, even if there's just one source that's continuously emitting from the site. And the point of this is that you cannot measure everything all the time, even with continuous monitoring systems. And so the next question then becomes, all right, what you have are observations of what the sensor detects. How do you translate observations into emissions information? What are you looking for? You want to know where the emissions are from, you want to know how big the emissions are, and you want to know if the emissions are fixable. So how do you go from observations, how do you interpret your observations to get you useful information? And a suite of projects that we've been working on over the past year will help you answer some of those tricky questions. It involves developing and thinking about dispersion models. It involves thinking about the performance of these continuous monitoring systems, and it involves thinking about how many different types of emission sources you have on your facilities. In fact, you will have a poster session at the end of today during the reception. The first 8 posters are exclusively talking about different aspects of this problem, understanding continuous monitoring systems and how do we interpret data from these technologies. You're going to also hear a lot more talks over the course of the next 2 days from Dr. Hammerling, Dr. Allen, and graduate student Colette Schissel, who will be again telling you more about some of the details of how we develop these understanding of the performance of continuous monitoring systems. The next project I'm going to give you an overview of, and this is not data, but this is more of an illustration of what field campaigns look like. As Dave said earlier, we've been involved in several methane emissions field campaigns around the country. We are involved in the Marcellus Basin. We are involved in the DJ Basin as well as the Permian Basin, and more to come in the next year. So what you're going to be seeing here are one such examples of how we think about methane emissions measurements and interpreting those emissions estimates that we get from different technologies. So this is an example of a study we are conducting in the Marcellus Basin. Different basins around the US have very different characteristics. So what you're going to be seeing here over the next 10 seconds are the different types of facilities that we are measuring methane emissions from. So this you're seeing here is a compressor station, and they are dispersed across the entire basin. And you can also see the terrain. It's complex. There are hills and there are forests, and it's much harder to measure methane here compared to other regions where you might not have such terrain. Here are wellheads. There are a number of them in sort of the western Pennsylvania region. But one of the characteristics of the Marcellus Basin is that it's not just oil and gas facilities that you're measuring methane emissions from. For example, what you're seeing on the video right now is a coal mine. And coal mines often have huge methane emissions, and what we're learning is that they can often be very variable. So if a satellite sees methane emission here, is it from a coal mine or is it from an oil and gas facility? Those are critical questions that we need to be answering. And the last type of site that you have in the Marcellus Basin are landfills. Landfills also emit methane, and they are a much more diffuse source. So how do we address and untangle methane emissions from all these different facility types? And for that, you want to use a suite of different technologies. As we saw before, every technology gives very different types of information you might want. This example are continuous monitoring systems. You just install them around the site, and it detects methane emissions continuously. You can also have aerial surveys. You have a plane that flies around and detects methane emissions over a large number of facilities. Apparently, in this animation, our planes cannot turn, but it does go to every single site in that region. But the point is, the advantage of planes is that it can cover a lot of ground in a fairly short amount of time, so that gives you a much larger picture of what the emissions are. But you cannot use some of these technologies if you have a source that's very diffuse, or if you want to measure methane emissions over a large area. So what we do are things like mass balance measurements. Essentially, you want to know what the methane emissions are from an entire region or from a very large site. So you just take a plane and measure methane concentrations around the site. And then you use something like mass balance approaches to estimate regional emissions. And the last thing, and I think a lot of us are excited about, are satellites. Satellites provide great coverage. Often you have satellites that come over a facility once a week or twice a week, and it gives you a lot of information much more regularly. And so one of the things that we want to think about is, how do we put data from all of this together? Data from continuous sensors, from aerial surveys, from satellites look very different. And so what you want to develop is collect all of the data from these technologies and develop a measurement-informed inventory. But that's also not the full picture. We are learning a lot more about what these emissions are. So you're seeing emissions pop up in the region. Each color corresponds to a different major equipment. And you can see how they vary in space and time. They just go, they're there for a few hours, and then they stop. Sometimes, when you measure, you see large emissions. And so if you zoom into these things, what you're seeing is a truck coming onto a facility. This is a maintenance event that's resulting in a large emission source. And the point of that is that it's not just enough to measure your emissions. You need to understand what operations are ongoing on the ground. That's why one of the things that we work really hard at is in every project is we try to work with all the operators in a collaborative way to understand what the methane emissions signatures tell us. So you have the measurements, and then you work with the operators to think about what those measurements mean. Because if you don't have that second picture of what's happening on the ground, you're not going to be able to interpret your measurements effectively. You might see a large emission, but the large emission could be from a maintenance event that happens once a year, or it could be from a leak source that happens continuously, and there are many of them. And you wouldn't know the difference until you work with operators and think about, why do we have these emissions, or where are these emissions coming from? And this is just an illustration, a cartoon of how we think about it, but you're going to hear more about exactly how we do this with specific projects and specific data over the course of the next 2 days. So you're going to have a number of talks focused on methane emissions measurements from different basins, as well as posters number 5, 6, 12, and 15. All right, so now we saw models, we saw measurements. What does this all mean for policy? How do we think about using all of these things that we learn for effective regulatory rulemaking? And one example I'm going to show is the FEAST model. The FEAST model stands for the Fugitive Emissions Abatement Simulation Tool. We developed this model to be able to compare leak detection and repair programs using different technologies. And so what happened in the past year or so is EPA took the feast model that was developed by EMDL researchers and developed what is called a matrix approach. Now, there's a lot of debate on whether the matrix is right or wrong, but the point is tools like this are helping move public policy forward right now. One of the key questions in the industry and over the past few years have been that can we use some of these new technologies, these aerial technologies, these satellites, the continuous monitoring systems, because they are more effective than some of the technologies we've been using in the past decade. But to be able to use those technologies, EPA had to come up with a way to find out that the new technologies will achieve your emissions reduction targets. And that's exactly what the EPA did with the feast model. So they used the model to simulate and model different technologies and came up with a framework that allows operators to use and deploy some of these new systems. In fact, most recently, and you'll hear more about this later, we developed a pipeline version of the feast model. So the Department of Transportation, PHMSA, recently came out with regulations to address methane emissions across pipelines, gathering pipelines, transmission pipelines, and distribution pipelines. So we developed a feast model that helps us understand the deployment of new technologies in the pipeline segment. And so this is the place where we bring all the information we learned from testing technologies, from the models, and from measurement campaigns, and put them together to understand what it means for public policies. And I'll talk a bit more about this later today as well, but this is one of the key ways where we want to take the work that we do here in research and translate it in a way that's broadly useful to stakeholders in the space. So over the course of the next 2 days, you're going to hear a lot more about this. What you're seeing here are the 5 different projects I started with, and what you're seeing at the bottom are all the posters and the talks that you're going to be hearing over the next 2 days that will provide a lot more detail than what I just showed you with these animations. All right, the one thing that Dave mentioned earlier is our role in convening experts in the space. And this is something we have the ability to do because we work with a lot of different stakeholders in the space to thinking about some of the key technical questions that we need to address going forward. So one example of bringing all of this together and how all of you can get engaged in this process is what's shown on this figure. It's called the Differentiated Gas Framework. So if many of you might know, the Department of Energy is participating in an international working group with 15 other countries, thinking about how can we develop a global framework for differentiated natural gas. That is, how can you trade natural gas in a way that provides additional incentives for reducing methane emissions. The summer of 2023, we organized a workshop with our colleagues at Center for Strategic and International Studies in Washington, D.C., that brought together experts from 15 different organizations that typically don't work together and often typically don't even agree with each other. We came together, we said, okay, this is happening. We need to address some of the key technical issues that are coming up in this differentiated gas space. What can we all agree on? And so what can we all agree on is what was that convening workshop was, and that's going to come out in Nature Energy in the next week or so. And all of you will have access to that information. But the goal of that workshop was identifying key technical challenges to implement a global differentiated gas framework. We didn't solve the problems. I don't think we could do that within the span of a 2-hour workshop, but we identified the key problems that we need to solve. And so what we are going to be doing, and you'll be hearing more about this from Dr. Erin Tullis later today, is that we are launching a differentiated gas road mapping initiatives. What will the initiative do? It's going to develop state-of-the-science review papers. It's going to write commentary, op-eds, and white papers. And it's going to develop tools and technical guidance. And so by this time next year, when you all come back to this conference, we want the theme of the meeting to be measurement-based differentiation of low emissions natural gas supply chains. And you'll hear a lot more about this in panels later today. And there'll also be many avenues for all of you to be engaged in throughout this process. We want this to be fast. The Department of Energy and other countries are moving fast on this. So we want to start having some of these outputs starting in the next 3 months. All right, so that's a very broad preview of some of the work we've been doing. As I said, you'll hear a lot more of the details from students and researchers who will be presenting posters and talks over the course of the next 2 days. So let's sort of step back a little bit and think about, let's say we do all of this and everything works out just as we intended. What will we have learned if we achieve our goals by 2030? As Dave said, if methane emissions ceases to be a problem in 2030, we have found ways to mitigate them as much as possible. What's going to happen next? And here's where I think this is one of the first things that we're doing that takes a complex problem, a complex supply chain, and think about how do you design an MRV system for a global product with complex supply chains. Monitoring, reporting, and verification is something that's very popular right now, and that's not just in the methane space. But methane and all of us in this room are ahead of almost every other topic and research area and field. We are ahead in terms of technologies that help us monitor methane emissions. We are ahead in terms of thinking about how do we report emissions from different parts of the world. And we are ahead of others in terms of thinking about how do we do this together as a community and have a global framework for understanding and mitigating methane emissions. And so if we are successful, if all the topics that we are working on are solved over the next 7 years, we will have demonstrated an MRV system for a global product with complex supply chains. That's never been done before. And the key part of this is MRV, the importance of MRV is just starting. Over the next years and decades, what you're going to see is this MRV topic come again and again and again in the context of new research fields that are just starting. You can think about hydrogen production and delivery. You can think about chemical manufacturing. You can think about carbon capture and storage. In fact, the Department of Energy is investing millions of dollars in MRV for carbon removal. All the lessons that we learned here in the methane space will be directly translatable to some of the new and upcoming research areas. So if we are successful here, we can help all of these other research areas that are growing rapidly in the United States and around the world to have an effective MRV system that can help us move towards our goals of net zero emissions by 2050. And that's really what we want to do here. So by the time you come back in 2024, in 2025, in 2026, you'll see how we are making progress on some of these ideas and concepts. And over time, we'll expand. We are starting with methane because we are the most ahead in terms of getting these solutions and tools out to the public, but this will expand to other areas of research. And in fact, now it's a good time for me to talk about what some of those other areas of research that the University of Texas at Austin is going to be working on. But to do that, I'm not going to talk about it myself. I'm going to invite Dr. Matt Bailoff from the Petroleum and Geosystems Engineering Department at the University of Texas at Austin. So until recently, he was also the chair of one of large research organizations, just like EEMDL, the Center for Subsurface Energy and Environment. And he stepped down to become chair of the department. But the Petroleum Engineering Department at UT Austin is expanding in all of the new areas of research that I just talked about. So without much ado, Matt, welcome.